Greetings, math friends. We are going to look at breaking the axioms for the real numbers in classical algebra. So these axioms you've probably seen most of at some point from third grade on in some way. Things like the additive identity. Any number that I add to zero gives me that number back. Distributive property, a wonderful tool that you can use in problem solving, and various others. There's about 14 of these rules, you could say. And one of the illustrations that I think other mathematicians like to use is that it's like a sport. These are the rules for how you play the game. If you change the set of rules, you're changing the game. You can think of this historically when we looked at Euclid's fifth postulate, which has become known as the parallel postulate. If you change that parallel postulate, you still have geometry. You just have a different geometry than the one that Euclid described in his book, The Elements. You could potentially have a hyperbolic geometry or a elliptical geometry. The reason I undertook trying to break these axioms is because my best friend, who is not a mathematician but is interested in mathematics and aerospace science, was asking me about these axioms and if they always held. And of course, I said they did not. It depended on the algebra. And that's equivalent to changing games and changing rules, or changing rules and getting new games. So he wanted to know examples of where these axioms didn't hold. Some of the mathematics that we look at is going to be beyond what many people have seen. Other people who have gone very deep in mathematics may have come across all of these things. But we're going to look at different situations where each of these axioms break. So the first one we are going to look at is the additive identity. The additive identity in the real numbers in a classical algebra is 0. So we're going to look at an abelian group. That just means that it's a algebraic structure that has commutativity. And when we look at this, we're going to have an operation that is the triangle plus operation. So this is addition, but it's addition with a twist. In this case, every time you add, noise is added to the system. For those interested in applications, a system like this might be similar to a system that's needed for those that are involved in differential privacy, in which we need to collect data from clients, but we need enough noise in the system that we can't identify which clients provided the data. Now, I'm not saying that this group is involved in that, but it's a toy model, perhaps, of those types of systems. In this case, whenever you add two numbers, you also add 2 to that calculation. So 2 triangle plus 6 is going to be 10. 6 plus 2 is 8, and then 2 again is 10. Now, for this, we find that the additive identity is -2. If I take 2 and I add -2 to it, we get 2 back. Because the triangle plus adds a 2, a -2 negates the noise that we added to the system. And this will work with other numbers as well. If we take -2, triangle plus 6, we get 6 back. So we see that every time we add -2 to a number in this system, we get the other number back. So -2 is our additive identity for this algebra, not 0. Multiplicative identity, there is a fun group that I came across when I was studying abstract algebra. It was in Joseph Gallien's Contemporary Abstract Algebra textbook. I quoted this out of the 8th edition. I'm not sure how many editions he included this group in, but this is a group with a modular arithmetic, and in this case it's mod 10. This is a finite group. There's only 4 elements in this group, 2, 4, 6, and 8. So when we multiply any result that we have to take modulo 10. So 2 times 6 is 12, but then mod 10, that is 2. In this group, it turns out that 6 is the multiplicative identity. I can multiply 6 by any number, including 6, and we get that number back. So 8 times 6 is 48, but 48 mod 10 is 8, so we have 8 times 6 is congruent to 8. 6 is the multiplicative identity for this group, not the number 1. The next one that we're going to do is additive inverse. And for this, we are going to use a tropical semifield. We're using a max plus algebra, which is a tropical semifield. And when we do addition in this, we take the maximum value of the 2 numbers that we're adding, and that is the result of the addition. Those of you interested in applications, this was used in computer science. In this case, because of the way addition works, subtraction doesn't really work in this system. In other words, there is no additive inverse for this system. You can try to do something to the effect of a subtraction and it just doesn't work out for you. This system uses the extended reals instead of the real number set to operate on as well. For multiplicative inverse, this one was difficult to find a nice example to work with. I'm happy to be working with the quaternions in this. If you've not gone beyond high school mathematics, you may not realize that there are numbers beyond the complex numbers. But there are, and the next number set up from the complex numbers is the quaternions. And we use this bold H here because they were developed by Rowan Hamilton in Ireland. So H is because of Hamilton's work with these numbers. But we're actually using a variant devised by David Rusin. And we're going to define the square of I to be -1 plus epsilon times j. And the epsilon is just going to be a small real number. Due to us defining I squared as -1 plus epsilon j instead of just -1, that breaks the system from being able to effectively have all multiplicative inverses for the numbers. If we try to find a multiplicative inverse in the normal way for a quaternion, we have this formula where we take the conjugate of the number and divide it by its magnitude. When we take that number and we multiply it back to the number that we started with, we find that it does not give us 1, which is the multiplicative identity for the real number system, which we are breaking. So no multiplicative inverse for this algebra because of this special definition for I squared. Breaking the commutativity of addition was also difficult. Most people pretty much accept that as a given, but we shouldn't just assume that the commutativity of addition is a given. In this one, we are going to look at a whole ternary ring. So we have a set of numbers, two operations, and a ternary operation. The operation that we have in this ternary ring is really a trinary operation, but it can be broken into two binary operations. Most people are very comfortable with a binary operation. You take two numbers, you do an operation on them, you get an output. Some people are also accustomed to an unary operation where you take one number and you do an operation and you get an output, like 2 factorial gives you 2, that you have one input and one output. This is a trinary operation where you have to have 3 inputs to get one output. But this breaks down into 2 binary operations, and that's the way we're defining the addition in this system. It's half of the trinary operation, sort of. So every 2 inputs that we have, it actually has a built-in third component to it. So A plus B really takes the A and the B and the number 1 and does the operation in here. And in this case, we are going to define the operation in such a way that we have some subset of the field. And if the M value is in that subset, we do one type of procedure. If it's not in that subset, we do a different type of procedure, and we have a mapping for that, which is this sigma. Sigma has to be a part of the rationals adjoin the square root of 2. So this is a subset of the real numbers. So we're really looking at the big set as real numbers, and then we have a subset of the real numbers, and we're going to do this operation. Because the position of the number helps define how it's used in the operation, if you change the position, you're going to potentially change the effect in the system, which is why this is now not a commutative addition. So A plus B is not going to be equal to B plus A because of the way that this system is going to be computed, because the middle number of the 3 numbers is defining one way that you're calculating the outcome. So order is important in the addition process here. For breaking the commutativity of multiplication, some of you may be familiar with this from Algebra 2 in high school. You may have been taught or come to realize that you cannot commute matrices when you're multiplying, because the order is important with the way that multiplication is defined with matrices. You see these examples. We take the same 2 matrices, we multiply them in both orders, and you get 2 different results, which are not the same matrix. Associativity of addition was difficult as well to break. Kind of related to trying to break the commutativity of addition. Associativity of addition, we just, I think, many times just take for granted, and it's not. We're going to look back at a whole ternary ring, this time a non-Desarguesian ring. For this example, we have several elements, 1 and 0, that are a part of this ring, so it's not an empty ring. And we're looking at a similar addition to the one that we had previously. I didn't put the circle around all the pluses in this one. There's a geometry behind this. It's related to affine and projective geometry interaction. So when we do these operations, there's a geometry behind it. So it's related to lines. So you see the annotation here that I have point AD is a part of the line 1B. The parentheses are the points, and then the square brackets are defining the line that it's associated with. planetmath.org had a nice beginning set of notes for these, and then if you want a nice explanation with some graphics, check out Casual Graphs. Has a nice video. So in the end, as we're looking at this as just single symbol representation, we end up at the end with this number E and number G, and number E and G are not the same because they're two different lines when we look at the geometry. So the order was important, essentially. You can't just group them however you want. For breaking the associativity of multiplication, again, we can go back to a high school level concept. If you were in like a pre-calculus, algebra 3 course, maybe even an algebra 2 course, or like high school physics, and you've talked about vectors. The cross product for vectors is closed under multiplication, but it's not associative. So you can't just group your vectors however you want and then do a cross product on them, because you end up with different vectors, and those obviously aren't the same if they're different vectors. For distributive property, we can break that because in the real numbers in a classical algebra, distributive property works from the left-hand side and the right-hand side, so we get a single distributive property rule there. In other algebras, you may only have a left-hand side or a right-hand side distributive property, or maybe you need to declare that you have both, like in a matrix algebra. You can have a left-hand or a right-hand distributive property with a matrix algebra, but you can't have one for both unless you have an identity matrix. So again, from a high school level, we can explain how to break distributive property with just the matrices. And you see a couple of examples there and the resulting matrices that are not equal. Essentially, all the axioms that require you to have an ordering break once you move beyond the real numbers. So once you move into the complex field of numbers, that algebra doesn't have a natural ordering to it. And there's proofs that you can do to show that. And as we look at the final axiom that shows a completeness to this well-ordered field of real numbers having a nice algebra on it, which we're systematically breaking, we look at just a subset of numbers, subset of the complex numbers. And we're just going to say that this subset is called S, and it has negative numbers, it has 0, it has positive numbers, it has irrational numbers, it has I. That's one of the things that we gain when we go to the complex numbers. So now, this axiom says we should be able to have a least upper bound. So there should be a number that we can say is the smallest number that is bigger than all the numbers in the set. So we have to know what the biggest number in the set is. We can order -2, 0, square root of 2, 3, pi, 5 very easily. Those are real numbers, and there's a nice ordering to the real numbers. But then you have this I. How do I place I in here? Is I smaller than -2? Is I larger than -2? Is I bigger or smaller than 0? Can you prove that it's smaller than 5? Because we can't prove that this has an ordering with this, we can't say what the least upper bound for a subset of these numbers are from the field of complex numbers. This is the same problem that we have with all the other ordering axioms. Because the complex numbers can't be put in a specific order in the same way that we do with the real numbers, then we have a problem of all of these axioms are just broken in some way. Hopefully this has helped you understand that the rules that you're using in algebra are specific to the algebra that you're working in. There's other algebras out there. That's one thing that I didn't know when I was in high school, and I think probably would have been interesting to know, is that there are these other algebras out there, and we're just learning a very specific one. I hope you find some mathematics in your part of the world to enjoy and share with others. Cheerful Calculations. Why do you have to be in the way? I'm trying to film. Yeah, you're causing me trouble because I'm trying to film. Unless you're going to teach this math course, you aren't supposed to be in the video. Oh, what's a tired puppy?